Hello everyone, welcome back to Machine Organization and Programming. This is going to be the first in a series of 6 lectures where we go into the pointer array equivalence. Essentially, they have a lot of things in common, but we're going to break down all the pieces and go through these one at a time in a sequence of videos to kind of build this up. All right, first up, we're going to be talking about pointers and the memory model. We'll begin with a little review. We began the course talking about programming in C. And so far we've covered the basics of control flow and data structures. So in control flow, we have conditionals like the if statement. Loops, we talked about the while loop, the do while loop, and the for loop, and just basic function calls. Also in this control flow section, we've got the switch statement. I'm not going to go into that. We're not going to deal with the switch very much other than it might be in some menus that I write for the homework assignments, but I'm not going to ask you guys to write one. It's there. Look up how to do it. Works the same as most other languages. But we're not going to be diving into that when we make the connection to assembly language. So I'm going to just skip over that. And then as far as data structures go, we covered the primitives. So we started looking at a char, int, float, and double, the 4 basic data types. Then last week we talked about how to create our very first one-dimensional arrays. Today we're going to be looking a little bit more at character arrays and the one little difference between character arrays and arrays of integers. And we introduced the idea of pointers. Today is going to be a deep dive into pointers and arrays. All right, some things coming up. I'm also going to skip over enums. They really go hand in hand with switches. There'll be some examples where I use these in the homework assignments. You'll see how they work. Look up how to use them if you're interested. We probably won't do more than that in this class. And then today we're going to spend about a third of the class talking about multidimensional arrays. In particular, the memory model, how C is going to, when the compiler runs, allocate memory on the stack or on the heap for these multidimensional arrays and primitive arrays too. We'll start with those. And then we'll wrap up with an introduction to structures. If you're familiar with classes from other object-oriented programming languages, structures are the C version of that. So C is not an object-oriented programming language. We don't have classes, but it's a composite data structure that lets us do things a lot like classes where you have containers for data, but it doesn't let us have functions that go along with them to process those pieces of data. So technically we're not creating objects, we're not having functions that operate on them, but we will have data packages. All right, I'm going to jump back over to a CSL machine. We'll pull up some code. And the way I want to approach this today is to just start off with a quick review, and we'll do some, experiments. I kind of want to show you guys, if you're trying to learn a brand new programming language on your own, how I approach this by just learning a little bit, try an experiment, and see what happens. And at the same time, we're going to try and learn about how the compiler is allocating memory to go along with all of these data structures. So that's the goal for today. Once again, let me hop over to a CSL machine and pull that up. All right, I'm back. I'm actually using PowerShell. This is my local machine. I was getting some truly horrible lag trying to deal with the CSL machine just now. And so I'm just going to scrap that and go with PowerShell. I don't have Vim installed on my computer, so I'll be using Notepad++. It's the lowest level editor that sort of gives me the features that I want. And I don't want to use a powerful IDE package today that might hide some of the details that as I want to remind myself what I need to talk about. So that's what I'm going to be doing for today. So as you can see here, I've got my teaching directory where I've created a demo.c file to get us started. When I compile this, this is going to go by really fast from now on. I'm using GCC as my compiler on this computer. If you guys don't have a C compiler installed in your Windows machine, I installed the mingw package to give me the Windows version of GCC. I'll go ahead and write a note to remind myself to put that in the description. It's kind of a pain to install. Just find some directions and go through those. Follow along with the directions and it'll get you there. All right, I named it demo.c. I'm going to be using the M32 to compile my code for 32-bit machines for everything I do today. This is going to give me 32-bit addresses when I look at all the addresses that are stored in pointers. It means that my pointers will be 4 bytes because that's 32 bits, as opposed to the default 64 bits that my machine's going to give me. And I'm going to have all the warnings turned on because I make tons of mistakes and I want to be able to talk about them and talk about good coding practice. All right, so let me just go ahead. We'll run the compiler right here. My demo program when I compile on a Windows machine, this is going to give me a .exe file for an executable file. And to run that, I need to use /demo.exe. And if you screw this up, if you're doing PowerShell, if you're trying to follow along on your own computer, it'll give you a message. So all this program does right now so far is print out welcome to week 3 of CS 354. Let me pull that up. I just wanted a framework to get started when I just needed to know that it compiled and I didn't have any dumb mistakes in there. All right, so I'm going to go ahead and I'm going to write a little bit of code. You guys can pause and copy the code in yourself as soon as I get this written. I'm hoping that if I just pause the recording, it'll speed it up a little bit for you guys. The video will be a little bit shorter. If you're reviewing this later, before the exam or something, you can watch it on double speed and not have to watch me type anything to get a good review. But at the same time, as you guys are going through watching this for the first time, you should have the video pulled up. And today is one of those days where you should follow along and do everything yourself. You're going to make little mistakes. You'll have typos in there. They're going to give you error messages. All of those are very informative. You'll learn a lot more by making a typo or getting a result that's different from what I get. I'm on a Windows machine. I'll explain what I see and why my compiler is doing what it's doing, why the memory is allocated a certain way. Your machine's probably going to be different. It's not going to use the same memory addresses. It might do things in a different order. And those are all very informative learning opportunities. And if you get something really, truly weird, throw it on Piazza and we'll go through it and break it down. And it's going to be a great opportunity for everybody in the class when those things come up. All right, so I'm going to pause now and write some code. All right, so I just finished writing a little bit of code. This first piece here, starting on line 7, we're just going to do a quick review of pointers and what they do, and then I want to take this and try and connect it very deeply to the memory model, what's going on inside the machine. So I'm just created two integers, a and b. I've given them some values, 3 and 4. Then I've created 2 pointers. Remember that anytime I have the name of a type, like int here, followed by a star, this is going to be the creation of a pointer. In a little bit, I'm going to be using just the star without the type there, and that's going to be dereferencing the pointer or following the pointer to the data. Okay, and this first pointer, PA, is a pointer to variable A, and I'm giving it the address of A so that it actually stores, pointers store memory addresses of other variables. Same thing for B. So I'm creating a pointer to variable B, so P for pointer, B for B, and giving it the address of B. Then I'm just going to be printing out everything I can possibly think of about these things. So for A and B, they're just integers. They contain a value. So %d is going to print the decimal version of that value right there in A. And I can print the address, and that's going to be %p to get the pointer code or something that's going to print in hexadecimal, I guess. And I'm going to give it the address of A. Remember, the ampersand is the address of operator. I'm going to do the exact same thing for B. I just wanted more than one thing, so when I draw the picture of the memory model, I've got like some actual stuff there, and it's not looking pretty empty. I'm going to do the same thing for my pointers, PA and PB. I'm going to print out everything I know about them. So first, I'm going to be dereferencing them, and because they're integer pointers, this will print a decimal value. The %d is the format code there. I'm also going to be printing the actual value, the contents of that pointer. And again, pointers store addresses, so I'm using %p to get a hexadecimal memory address. And then I'm going to print the address of PA, where this is actually stored. So here's the dereference, here's the actual contents, and then this is the address of PA, or where PA is stored in memory. And then the exact same thing for PB. All right, let me pop back over to PowerShell. I just got this to work, I tested it, I didn't make any mistakes. So here's what we're looking at. A contains 3, B contains 4. That's exactly what I initialized them to. That's looking pretty good. We can see that it's storing A at hexadecimal value 0061FF1C. From now on, I'm going to abbreviate these. I'm just going to be talking about the FF1C, or maybe even just 1C, because they're all going to be really close together, and I don't need the leading digits there. I mean, all of these, 0061FF, 0061FF. I'm going to stop repeating that. And until we're getting to, all of these memory addresses are on the stack. They're all very close together. When we have memory addresses for things that are not on the stack, then I'm going to highlight the difference, and the leading digits will be different in that case. All right, and again, let's see here. I'll pause it for a second. Just which one of these is bigger? Is 0061FF1C greater than or smaller than FF18? Which one comes first? Just pause the video, make a guess, figure it out. When you draw the picture of the memory in just a second, I want to make sure I put all of these in the exact right order so you guys can check and make sure that it matches. All right, and then with the pointers, so I've got a pointer here. When I dereference it, that means follow the address stored at that pointer and go get the actual data. So that's 3. It's a pointer to A. It's getting that number right there. The actual pointer contains an address. So 0061FF1C, this address right here is the address of variable A. So this was the address of A. That's the value contained in this piece of data right there in that memory location. And the address of PA is, so PA is a pointer. It stores a memory address. It's actually located in memory itself. And I can go get the memory address where it's stored. I can see here this is at FF14. Again, is this bigger or smaller than FF1C, FF18? I want to make sure I put these in the right order, so you guys need to check me. All right, and then same kind of thing for PB. It contains the value 4. The address it points to, 18, is the address of B. Perfect. And again, it's got its own memory location. In this case, FF10. All right, so I'm going to just pause the video. I'm going to go pull up a PowerPoint slide, and I'm going to, actually, let me grab a screenshot of this one right now. Pull this up in PowerPoint and draw a picture of what's going on in the memory. 1 second. All right, guys, I just started making this picture using the PowerShell data, and I was trying to put these addresses in. I'll show you that slide in a minute. But this just struck me as really weird that these were so small. I mean, they're starting with 00. Now let me take a look at this. I haven't introduced this idea yet, but all of the space, all of the memory that your program gets is divided up into a bunch of sections. Up at the very top, like address 0 is reserved. We can't use address 0. And I'll talk a little bit about that. We're frequently going to set uninitialized pointers to address 0 because it cannot be used. We cannot write there. And that way we will know that that pointer is uninitialized. It'll cause the code to crash. And crashing is better than weird random errors that are unpredictable. So that's like safety. We'll talk about that in the null pointer section coming up soon. Then after this reserved memory, is memory reserved for the actual instructions. When I compile my code, it generates those binary numbers that represent the instructions. The CPU fetches, decodes, and executes them. Those are stored up at the top at very low memory addresses. Below that, below the code section, and I should also mention that sometimes the operating system, for security reasons, will offset this code by a random amount, so it makes the addresses unpredictable. So address space randomization means that it's a lot harder for someone to hack your computer if they don't know where the instructions are. And they'll just put a bunch of like reserved blank space in between the code and address 0. All right, so this is unpredictable where this is in general. Following the code, oh, by the way, if you get the chance, computer security is an amazing class. I highly recommend it. 640 or something like that. I might have the number wrong. Great class. Anyway, after the code section, the compiler is going to reserve space for any of the text that's hard-coded into the program. Like right here, I've got this welcome to week 3 of CS354. That code, the representation of that text is going to be in this section right here for text and for global variables. Anything that I need, that I know I'm reserving space for global variable, will be in this section up here because it's going to be accessible to any of the functions. Below the text section, we have the heap. The heap is for dynamically allocated memory. That's next week's topic. Right now, we are not using the heap. It should remain at size 0. We're not using any of it. But as we dynamically allocate more and more memory, it's going to grow from address 0 up the top here to larger and larger numbers. The rest of the memory is the stack. Now, the stack is where all of the functions are going to reserve memory for their local variables, for parameters. I've got the list right here. For parameters, for local variables, and returning information. And the kinds of things it needs, if it's a function that has a return value, it'll reserve space for that return value. Like main, for example, returns an integer. It also needs to know the return address, so where to jump to. In this case, PowerShell is going to be the bottommost frame. PowerShell is what I'm using to call my demo demo.c or demo.exe function, and that has a main function. So when main is done running, it's going to return 0 and go back to PowerShell. So there's a return address into PowerShell's code, so it knows where to go. Anyway, we don't have any parameters. There was no command line arguments, so that's all going to be just 0. For his local variables, I don't have an array yet. That's coming soon, but I do have A, B, PA, and PB. So those are the local variables. They're going to be stored on the stack. Now this typically starts out at really enormous addresses, the end of the address space, and grows towards smaller numbers. If I write a function in main and call that function, or if I call a function from main, it's going to get a new stack frame or a new activation record with all these things. It's going to have space for parameters. They're going to reserve space for local variables, return information, again, the return address, the return value, some pointer information to remember where all of how big the stack frame in main is. That'd be the base pointer. We'll come to that in the middle third of the class as we break down what happens with a function call. But so this struck me as really weird that it starts with 0, 0, because the stack starts at the very, very largest addresses. And apparently PowerShell is just not giving my program very much space to run. It doesn't need very much space. It's got 4 variables and just prints them out. It doesn't need it. We're not using a huge amount of memory. But it seems weird to me. And so I wanted to go and compare it to what happens when I do log into a CSL machine. The lag was still bad. I'm going to stick with PowerShell for the rest of this lecture. But there's some differences. So on the Windows machine on PowerShell, the blue one, I'm using mingw as my compiler, which mimics the GCC that we see on the Linux machines. The Linux machines, of course, is using GCC, the GNU-C compiler. Here I'm using the same command, mem32, all the warnings, same file name, same file, just copied it over to the CSL machine. It's printing the same stuff. But now check this out. So A is still at value 3. That's good. Address of A is now, and again, here's the difference. It's printing the 0x when we use the GCC compiler. So printf on the Linux machines is slightly different than the printf on the mingw compiler, because this did not print the 0x for the hexadecimal. And it's also using the much larger address space. This is an image I can't highlight, but it's starting at FF, the very largest, bottommost addresses that are available. And FF, and all these start out 0061, 0061, nowhere near the end of the address space. Okay, second difference, when you count by 4s, because all of these, a pointer is 4 bytes, an integer is 4 bytes on a 32-bit machine. So we'll start with 10, 4 bytes later is 14, 4 bytes after that is 18, 4 bytes after that is 1C. It starts out here with the, PB, the pointer that I defined last, is at the lowest address. And so 10, 14, 18, 1C. It's just counting up in that order. Now check this out. Maybe a little easier to see, we've got 90, 94, 98. They're in the reverse order. So the takeaway message from this experiment is that the compiler has a lot of control over where it's deciding to choose to put things. The writers of compilers at some point needed to make a decision. So I have a function, it's in this case main, it's reserving some space for some local variables. Where am I going to put those? What order am I going to put them in? And so they had to make a decision about what order they went in, and clearly the writers of this compiler chose a different order than the writers of this compiler. They're backwards. All right, for the rest of this lecture, I'm going to continue using PowerShell and Notepad++, the Windows machine version. Be aware that there are some differences. If anything strikes me as weird that I suspect will be different, I will go back over to the CSL, deal with the lag. I know I can edit all of that out, and you guys will never even know that it's pretty bad today. And now that I think about it, I wonder if the lag is coming from my son's room where he's playing video games. It might not even be the CSL. It could really be my local problem. But I'm going to keep going with the local machine, and anywhere there's a difference, I'm going to pause and point that out. All right, 1 sec. All right, guys, I just put these things into a PowerPoint picture of the memory. So what we're looking at right here, this is the screenshot from the output from my very short pointer review program. Over here, I've got a picture of what's going on in memory. Now, memory in the computer is just a linear array from address 0 up through some maximum value of addresses. And each of those addresses will be holding 1 byte, so 8 bits of data. I've got these blocked into groups of 4 because all of the data that I'm looking at right now are either integers or pointers, and those are all 4 bytes. In memory, each of these, each byte is going to be represented by 2 hexadecimal bits. So there's 00, 61, FF, 818. Means that we've got all 32 bits accounted for in hexadecimal, or 8 hex digits. And again, as I've got the picture here, I've abbreviated all of my addresses. This 00 right here, I intend this to be 0061FF and then 00. And so like right here, I've got 1C. If I go down to this 1C right here where I've got variable A is going to be this 0061FF. I left off the 0061FF just to shorten this all up. So at 1C, I've got the data for variable A. And what's in this location is just the number 3. And again, in binary, that's going to be 32 bits. The first 30 of them are going to be zeros, and then we've got 1, 1. And again, for B, this is going to be a binary. It's going to have 29 zeros, followed by a 1, and then followed by 2 zeros after that. When the computer uses this memory, it doesn't know how many digits we have. It doesn't know how many significant figures there are. It always uses all 32 bits. That was one of the questions that came up on Piazza, and I just want to make sure that everybody gets that message that even though it's a number that's only like 3, very small, it still uses the exact same amount of memory as 30 million does. And every calculation the computer does, all of the bits go through. So if I add 3 plus 4 together, all 32 bits go into the adder for both 3 and 4. It adds the first 30 zeros together. It adds the first 29 zeros together for A and B. They're all there. They're just used in parallel, so it's very fast. Okay, so anyway, that's my picture here. I've got the memory addresses here on the left. I've got the data that they're contained. And then I jotted down, and in fact, maybe I should put these in parentheses just to kind of remind us that after the compiler runs, these names are no longer needed. They're completely obsolete. The compiler doesn't keep this. The only thing the machine cares about is the memory address. That's what it's using for all of the names. It doesn't care about A, B, PA, PB. It only uses memory addresses, 0061FF18. And they get replaced. Essentially what the compiler does, first time it goes through it sees int A, it's going to say, okay, I need to remember A. So it puts it in what's known as the symbol table. And then it says, okay, it's an integer, go grab 4 bytes from memory somewhere, and says, all right, let's, here we go, here's 1C. And it just remembers that A is in the code, the computer needs to know 1C, and it gets replaced. By the time this is compiled, and you're looking at the binary code that's executable, there is no A anymore. That's gone. It's all been replaced with 0061FF1C. Anywhere there's an A, it's now that binary code for that address. Anyway, but I jotted these down to make it easier to understand that this is where things are going. All right, next up, so A contains 3, B is 4. I've got these addresses. On the Windows machine, this is in the reverse order that I declared them. On the Linux machine, they were backwards from this at different addresses, but I'm sticking with this version. All right, and then when I've got my pointers at FF14, I've got the pointer A, PA. This contains a memory address. So this address, 0061FF1C, check it out. Let me see if I can highlight and get it to show up. It doesn't work. Okay, so this 1C is actually this 1C over here. I really hope my mouse pointer is recording because this is going to be a lot of garbage if it's not. You can't see where I'm indicating. Yeah, that 1C and that 1C are the same. So let me see. Let me grab an arrow. One sec. I think I can do this pretty fast. Where's the arrow? We need the good arrow. There it is. Top that down. So right there. PA. Shrink it. Points to right there. So anytime I use the star, so PA, the compiler sees a PA, it goes, it grabs this address right here. It's got this data, this address, 0061FF1C. The star says, okay, now go to that address. So it goes, I've got 1C, it goes to 1C right here, and then gets that 3. That's what the star means. It says, go get the address, and then follow that address and get to that number. All right, I've got another pointer here. I'm just gonna real quick make this a little more confusing. We'll add a second arrow because PB is pointing to that spot right there. I know I've got two arrows on top of each other. Hopefully that's not too confusing the way I built it up. Maybe you guys let me know if it is in the comments, and I'll stop doing that. If it works, don't do anything. All right, so next up, I feel like this is a great introduction to pointers. The next thing I'm going to do is go put together an array in memory. We'll print that out, and we'll look at all the same information, and we'll start talking about how the computer is going to deal with arrays.